Resistors in series and parallel. Resistors are used in circuits to control currents and changes in potential across different circuit components. They can be connected in several different ways, but we shall focus on the two most important ones. When resistors are connected end to end, such that any two adjacent resistors share only one common connection between them, the resistors are said to be in series connection. When resistors are connected such that the ends of the resistors are shorted together, which means that they are connected by zero resistance, the resistors are said to be in parallel. There are some important points to remember here. Number one, when resistors are connected in series, the same current flows through all of them, but the potential drops across each resistor depends on the value of the resistance. Number two, when resistors are connected in parallel, the voltage drop across all of them remains the same. However, the current flowing through each of them is distinct and depends on the magnitude of each resistance. An easy way to remember this is the phrase, a series circuit splits the voltage while a parallel circuit splits the current. Next, the larger voltage drop across the larger resistance in a series circuit. Next, the larger current flows through the lower resistance. Thus, in a parallel circuit, the smallest resistor will be carrying the highest current and vice versa. The sum of all the voltage drops across all the resistors in a series circuit is equal to the total potential offered by the battery. On the other hand, the sum of all currents in a parallel arrangement of resistors is equal to the total current being supplied by the battery. Now let's use this information to derive the equivalent resistances of series and parallel resistor combinations. In the adjoining figure, we have three resistances R1, R2 and R3 connected in series, being fed by a voltage source V. As this is a series combination, the current flowing through all three resistors is identical. Also, the sum of the potential drops for each resistor, namely V1, V2 and V3, will be equal to the voltage of the battery. Thus, V is equal to V1 plus V2 plus V3. Or we can say that I multiplied by R equivalent is equal to I multiplied by R1 plus I multiplied by R2 plus I multiplied by R3. So we can take I common here. IR is equal to I bracket R1 plus R2 plus R3. We can remove I from both sides of this equation, which gives us R equivalent is equal to R1 plus R2 plus R3. Thus, we see that in a series circuit, the equivalent resistance of a set of resistors is equal to the algebraic sum of their individual resistances. We shall now see what goes on in a parallel arrangement. In the adjoining figure, we note that the potential drop across all three resistors is the same and is equal to the potential offered by the battery. This is a property of any component which is placed in parallel with a battery. But the current in each resistor is different, as this depends on the individual resistances. At the common connection point on the left, the current splits into three values, then recombines at the common connection point on the right. Thus, the current in each resistor can be given as I1 is equal to V upon R1, I2 is equal to V upon R2 and so on. Now, the sum of all of these currents can be modeled as being equal to I, or I is equal to I1 plus I2 and so on. We can rewrite this expression as V upon R equivalent is equal to V upon R1 plus V upon R2 and so on. Since V is common to both sides of this equation, we can remove it and this gives us a new expression 1 upon R equivalent is equal to 1 upon R1 plus 1 upon R2 and so on. In this case, there are three resistances, so till 1 upon R3. This gives us the equivalent resistance of a parallel network. Now let us try some simple numerical problems to internalize the concepts we just learned. Take a look at the figure. In this figure, we have a battery supplying 4 volts of potential and there are 4 resistances, each of value 1 ohm. And as you can see, all 4 are connected in series. Now we have 2 questions here. Number 1, what is the equivalent resistance of this circuit? And the second, what is the current flowing in this circuit? Let us recall what we have learned. In a series circuit, the current flowing through all the resistors will remain the same. And the total equivalent resistance of this circuit is simply equal to the algebraic sum of the individual resistances. So here we have 4 resistors, each of value 1 ohm. So if you add them all up, you get 4 ohms. So the equivalent resistance of this circuit is 4 ohms. Now coming back to the question of current, we know that the ratio of voltage in a circuit to the resistance of the circuit gives us current. So 4 volts divided by 4 ohms gives us 1 ampere. And it is the same current of 1 ampere that is flowing in and out of each of these 4 resistances. Now let us modify this circuit, and instead of connecting all of these resistances in series, we connect these 4 resistances in parallel, which means that we are shorting the ends of all of these 4 resistances together. They have 2 common connections on each side. So the current will enter the common connection on one side, split into 4 parts, then recombine on the other. We know from the rules we just learned that the equivalent of this circuit, the resistance equivalent, can be found out from the relationship 1 upon R equivalent is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3 and so on. So here, since the resistances are 1 ohm each, 1 upon 1 plus 1 upon 1 plus 1 upon 1 plus 1 upon 1 is equal to not R equivalent, 1 upon R equivalent. So 1 upon R equivalent is equal to 4 in this case. So we now have to take a reciprocal. This is the step many students forget. You have to take the reciprocal. R equivalent is equal to 1 upon 4 or 0.25 ohms. So you can see that in the case of a parallel connection, the equivalent resistance is actually lower than any individual resistance in that circuit. In the common household circuits, you will notice that while it is easier to connect everything in series in your house, it is advisable to go to the trouble and expense of making all your connections in parallel. And the reason should be obvious after a little thought. In a series circuit, there is only one, remember, just one path for the current to flow. If the circuit breaks anywhere, if any of the individual resistances burns out or is rendered inoperable, the entire circuit will shut down because there is no alternate method for the current to flow. In a parallel connection, which while more costly because you need more wiring, has the advantage that if any one device in the house fails, all the other devices have independent power connections. So they can all function independently of each other. This is why we go to the trouble of connecting all household electrical devices in parallel.